infectious disease, talked about the epidemic curve, and now we're going to talk about study designs and a bunch of other things. So here we go. I'm going to share my screen. Where are you? There we are. And we're going to move on to lecture 2, study designs continued. Close this part. And first thing we're going to talk about, and this is kind of relates back to the SIR concept that we introduced in the last lecture, namely that people travel through different states. They flow from being susceptible to being infected to being recovered and or died. And this has broader implications for infectious disease, and we're going to talk a little bit about infectious disease flows. And one way to think about this is as a bathtub model. And so basically you have incidence of disease, it's throwing cases into this bathtub, and prevalence is either increasing or decreasing depending on the rate of flow out and the rate of flow in, right? So if there's a big drain, right, and flows are allowed to go out, mainly that people recover very quickly from their infectious state, then the bathtub won't hold much water, and so prevalence will be low. If incidence is much higher than the outflows, then prevalence can go up. So we're talking inflows and outflows, and how many cases get collected in one area at one time. So reporting of notifiable diseases at sentinel sites, right? That's incidence. Cases happen. Cross-sectional surveys or seroepidemiology, that's prevalence and number of cases at any particular time. And then deaths or cures are from vital registry data or hospital records. So bathtub model, and we've got 3 different sorts of ways of using the data from the bathtub model for different types of studies. So time periods to remember. Remember when we talked about last time, we talked about exposure and how it progresses over time. There's a latent period, an incubation period, and you got an infectious period. And there's this might not necessarily overlap with a period of symptoms or period of clinical disease. And that can differ from patient to patient. But what we see here is we got 2 patients here, and one has infected the other, we assume. And so their periods are slightly staggered from one another. And it's going to have different implications for transmission overall. But remember these important terms: latency period, incubation period, infection, period of infection, infectious period, and a period of clinical disease. And so the infectious disease incidence prevalence relationship, key relationships in infectious disease epi is the dependence of infection events among individuals and given populations. This is termed somewhat awkwardly dependent happenings. Individuals are all different, and their variability can have implication for disease transmission overall, and we're going to keep seeing that over and over again. But generally speaking, in a perfectly mixed population, incidence at time t equals the contact rate times the probability of transmission, and the probability at time t is the prevalence of infectious persons at time t. And we're going to see this when we move to infectious disease modeling later, when we break out the SIR model into its different components. This is sort of one of the components that we'd be looking at. Incidence and prevalence are related to one another. More prevalent cases means higher incidence of disease. Fewer prevalent cases means lower incidence of disease. And the contact rate between all those cases makes a difference too. And of course, the probability of transmission makes difference too. So, point is to take home from this slide is that number of infecteds at any particular time is dependent on these 3 factors. This relationship allows us to think about two types of risk factors: exposure to infection and susceptibility to infection. So number of infecteds at time t is related to the contact rate times the probability of transmission times the number of prevalent cases at time t. The right side all relates to exposure to infection. Behavior change programs could therefore, misspelling here, going to correct that, target things like reducing the contact rate, which we can see the contact rate goes down, the number of infected people goes down, altering the transmission probability. So for example, HIV, one effect of antiretrovirals is to reduce the probability of transmission from one person to another given contact. So we'll be reducing transmission probability. Or implementing things like condom use programs. That could be one as well. Or masks for COVID-19. Reduces the probability of transmission from an infected person to another person. And finally, reducing the probability of contact with an infectious person. So we have prevalent cases at time t, we sequester those people, keep them at home. So I've already sort of illustrated examples of each strategy: reducing contact rate, keeping people socially distanced, for example, altering the transmission probability, using things like masks, for example, reducing probability of contact with an infectious person, keeping people at home when they're sick. All these things can go in and change the number of infected people at any particular time. Importantly, this relationship does not assume equilibrium and works perfectly well in epidemic growth and decay phases. So it doesn't matter at what point of the epidemic we're talking about, this formula still holds. Mainly because it includes the prevalent cases at time t. So as that changes, it's going to change the impacts for the number of infecteds. It also allows estimation of each quantity depending on the data in hand and to inform study design. So it's quite easy to calculate given data that we might have. Some of this, probability of transmission, we might have to estimate somehow, or we might use some data that we have existed to estimate it somehow. And obviously, this can't always be known. But we can always get as complicated or as simple as we need to be. And we're going to talk about this later when we talk about infectious disease transmission modeling. Contact rates are hard to measure, but CP is just IT divided by PT. So we can also use that. If we know the number of prevalent cases, number of infectives, we can calculate the product of these other two things. R naught versus dependent happenings. R naught is specifically focused on number of new cases on average. So the number R naught, just to refresh you, is the number of new cases that arise from each individual case of disease. R naught equals CP times D, contact rate, times the transmission probability, times the human density. In contrast, dependent happenings are infect number of infecteds, times the contact rate, times the probability of transmission, times the number of prevalent cases. So we're not just talking density. Focuses on susceptibility and probability of infection per unit time. So we're looking at each individual time step here. And we're going to talk a lot about this when we get to transmission model. In reality, dependent happenings relationship is rarely used directly. However, it's a very useful framework to think about using the data on hand, data to be collected, study outcomes, and I would put D on here. Sorry, C. D on here, potential interventions. So, it's one of these things where it's somewhat of a mathematical exercise, but these mathematical exercises can inform how we behave and how we react to certain things. Like the curve that we see for COVID-19 is a model. It's helping us to guide, to look at what's going on in nature and provide some type of guide so we can help develop some understanding, so it can inform how we react to it. What sort of interventions we might create in reaction to that. And then there's non-mixing, right? So this is one thing, we're sort of jumping the gun a little bit here on transmission modeling. But assuming random mixing, that is, all people are likely to have as much contact with everyone else as anyone else, this really rarely occurs. People rarely mix in a uniform manner. They tend to be sort of clustered within their schools or their colleges or their families, their churches or whatever. They're not necessarily having contact with everyone. And we see this a lot in the United States amongst socioeconomic groups, amongst racial groups, where people will have limited contact with groups outside their own in-group. And this is one thing we're seeing a lot in COVID-19. The contact patterns among wealthy people are very different than the contact patterns among poor people and among racial minorities in urban settings. And so this is having vast implications on the dynamics of transmission of COVID-19. We're seeing that cases are appearing in poor neighborhoods, for example, and not in wealthy neighborhoods, because their contact patterns are different and they're not in contact necessarily with each other. So we're going to talk about this a lot more later when we get to transmission modeling. I keep saying that over and over again, which begs the question, why am I doing this lecture? But I want to introduce these concepts before we get there, get you thinking about it. And then there's other strange things like with sexual partnership units, which I mean, as we know, sexual partnerships vary between individuals greatly, vary between genders and sexual identities and sexual subcultures. Some people can have very limited contact with people, fully monogamous relationships. And other people can have many partners. Other people can have partners that overlap. They can have serial monogamy. There's all different kinds of things that can come into changing the way that contact patterns occur and changing the way that we would calculate something like the number of infectives at time t using that handy dandy formula we have before. Local effects can happen. Subpopulations can keep or not well above unity when aggregate data show elimination should be occurring. These are termed hotspots or core groups. You definitely see this a lot with sexually transmitted diseases. Some core groups have high levels of sexual contact, of serial partners, and they continue as hotspots, whereas others do not. Chain of transmission is only as weak as the strongest link. So part of our job as epidemiologists and public health people is to find that strong link and break it, and then potentially break transmission overall. So when we talk about assessing risk, what are we talking about, right? We have risk factors for exposure to pathogens. We have risk factors for infection after exposure. Remember, infection does not behave the same way in every single individual, and often is predictable even within groups, because they have different sort of physiological profiles or immune profiles, for example, or have sort of other related behaviors. Risk factors for clinical illness after infection. Again, individuals are all different. Risk factors for outcome, resolution, severe disease, or mortality after clinical illness. And we're seeing this a lot in COVID-19. Some people are at higher risk for mortality given infection, even given the initial similar symptomatic profiles. So when we talk about risk, we can talk about a lot of different types of things: exposure to pathogens, risk factors for infection, risk factors for clinical illness, risk factors for outcome. And this is where studies come in. Case control studies. Why do we do this? We talked about this last time in the last lecture. Why? Cheap, fast, fairly easy. Hypothesis generating in the face of unknown pathogens or unexpected transmission pathways. Remember, we talked about case control studies are good for assessing links between exposure and disease, right? We're comparing people who are cases who've been infected with people who have not. and comparing their different types of exposures and risk factors. When we do this, as we said last time, if time is of the essence, where cases are rare, it's sort of a quick and dirty method you can use to assess exposure profiles and different risk factors. Works less well when exposure is rare, unless you have this just absolutely giant sample size, which obviously most of us do not have the luxury to get. So we want to assess risk. Case control studies are a good option to go to. Case control studies caveats, as we talked about last time, cases require clear and unambiguous case definition. And in terms of infectious disease, this can sometimes be pretty simple to do. We might know that this person is infected and this person is not. Now, when we start talking about symptomatic profiles and other sort of outcomes that we might be interested in, becomes a little more difficult. Sometimes it becomes difficult when diseases are difficult to detect, or they might have like long latency periods where they're infected and we don't know. We definitely saw this in COVID-19. Controls, we have many options that we can choose from: neighborhood, family, all have issues. Everything you do in any study has positives and negatives, pros and cons. There are problems with everything. You just sort of pick the best, worst, option that you can find. Matching, you can increase your number of controls per case. And you see this a lot where people match 2 to 1 or 3 to 1. Maximizes power, but costs money. And other provides no information on temporality or causality, or simply comparing risk profiles between diseased and non-diseased people. Cohort designs are less common in infectious disease epidemiology. You see them a lot for chronic disease exposures, chronic disease outcomes, because they take time. In ID, we often don't have a whole lot of time. We're often dealing with outbreak scenarios. Don't have a whole lot of time to wait around for people to become infected. But that being said, it's not unheard of, especially with things like HIV. Used for vaccine efficacy and STI transmission studies. Follow cohorts to see if they've been infected with STIs. Again, HIV, is potentially one of these. Cohorts of individuals can be assembled within large spatial units, town, city, or country, or smaller households forming mid cohorts. Cohorts can be composed entirely of exposed persons, case contact studies, infected persons, pathogen shedding or infectivity studies, or just simply susceptible persons watching to see if they become exposed at some point. Cohort studies are great, but they're expensive. As we said last time, take time. Cohort designs, what can it tell you? Here's a pediatric dengue cohort. 4,000 children aged 2 to 12. We're looking at time to seropositivity. Changes in immunity and demographics strongly impacted DENV transmission in Nicaragua. Population level measures of transmission intensity are dynamic and thus challenging to use to guide vaccine implementation locally and globally. And so what we see here is that we've got a cohort. We're following along to see at what age they become infected, become seropositive, and when it happens. So not unheard of to do for ID research, but not particularly common either, but you definitely will see it. Case designs. This is one I don't think we talked about last time. Fairly novel. They're kind of new, somewhat in vogue. Relies on pathogen typing methods to compare between syndromes by pathogen. So if you want to learn about different sort of genotypes of different pathogens and look at different sort of outcomes within the individuals, this is one way to do it, comparing cases to cases. Let's say the pathogen of interest is influenza A. Records from all other ARI cases can be compared as controls, and like, all these different types. Benefits are it saves time and energy in data collection. The issues, limited specific syndromes, pathogen, bias from referral mechanism may also underestimate risk if there are shared risk factors. So, we can talk about case controls, but depending on what we're interested in, we might want to compare cases to cases. Here's a case design. Cases were infected with Campylobacter coli. Controls were infected with Campylobacter jejuni. And we got approximately a 10-to-1 ratio of controls to cases. And then we're comparing individual risk exposures for these two pathogens. So case control, case, very similar, sort of different goals. Data types to consider when you're talking about study designs or any sort of analysis of infectious disease is the assessment of exposure, proximity to case, self-reports, direct measurement. Sometimes exposures are difficult to assess, and you're sort of responding, your response is only going to be as good as the question asked. So you have to be very careful and figure out how to strategically get at the information you want. Self-reports, especially with sexual counters, can be somewhat unreliable sometimes. Recall bias can be a very, very big problem, particularly with like foodborne exposures. People can't remember what they ate 2 days ago, let alone 2 weeks, let alone a month. I know I can't. I can barely remember what I ate an hour ago. Assessment of outcomes can be challenging. Self-report symptoms can be difficult because often, people have an idea of what, a fever is like or whatever, but they don't understand, or they don't even know when there's a subclinical symptoms going on. And sometimes they don't know the specific sort of terminology to be able to describe what a doctor might be looking for. So that can be challenging. Clinical record review can be a challenge because misreporting, like people get busy, they don't record things properly. So there's a lot in Kenya. People are busy, they just sort of fill in the blanks and move on. And sometimes they don't fill in the blanks. And then you're left with sort of guesswork. Assessment of severity of an outcome, again, self-report. What's severe pain to one person might be not as severe to another person. Clinical notes, hospital records, like when we look at the mortality data, it's been in the news about COVID-19. What's the reporting can vary depending on doctor, depending on locality, depending on state. Measurement scales vary between studies. So you have to consider all these different things. General outcome options in your study can be things like incidence, which can use existing reporting systems, particularly for reportable diseases. Maybe easier and simpler, but biases are possible, especially where cases are not caught or reported. People with mild symptoms might not report. Prevalence generally requires study-specific data collection. Exception would be blood bank serology, where blood samples are taken in and tested for whatever. Most relevant for interventional studies, cost and logistics drive the decision. Now, obviously, any sort of epidemiologic study, money talks. The more money you have, the better study you can do. The less money you have, the more challenges you have, but you can be strategic about what you do. Okay, so this wraps up lecture 2 of week 3. Hope you enjoyed it. We're going to move on to lecture 3. If you have any questions, please reach out to myself or Tia. We're happy to help you. Hope you all are well. Hope you had a great Labor Day weekend, and we will talk to you later.